Hello, and welcome to today's class. I want us to look at the concept of machines. But this topic is a broad topic, and we're going to split this machine bit by bit. In this video, I'm going to look at the definition of machines, the examples of machines, the types of machines we have. Maybe you will look at just a type of machine. Please follow me on the other lessons where I'll be dropping the different types of machine. The only difference between one machine and the other type is the velocity ratio. So let's take it up. Now we take the definition of a machine. What is a machine? And we can always say that yes, a machine is a device that can make work easier, any device that can make work faster, any device that can make work efficient. That machine, that device or that tool is defined as a machine. Or we can say that yes, a machine is any device that can be used to overcome a large load, large weight, large resistance by just a small force. Of course, with the aid of machine, we tend to reduce more work done by a person we tend to reduce it using different machines. Now, these machines, if we look at some of the examples of these machines are applied in various sectors of life, various aspects of life. In our offices, we have machines there. Even in schools, we have machines. In the industries, we have machines, and they have their various uses. For example, in the offices, stapler is a machine. We have printers, they are machines that can help to make work very easy, fast, and efficient. Now, in industries, we can have spanners. Even in a construction site, we have spades, we have shovels, we have rakes. These are machines. They serve various purposes. So, any type of machine you require or you desire is dependent on where you want to use it. And then there are machines that can serve for various purposes. Now, let us look at some of the terms that we use in machines. One of the terms we use in machine is the one we call the velocity ratio. Now, velocity ratio is nothing but the ratio of distance moved by effort. Distance moved by effort. Or this one we can say XE, distance moved by the effort. The ratio of distance moved by the effort to distance moved by the load. We can say XL. Now, in other words, you can say that yes, velocity ratio, generally, velocity ratio is distance moved by the effort, followed by the distance moved by the load. Now, we can have the second one, which is the mechanical advantage. We can use short form here, VR, and I can use short form here, mechanical advantage. Now, this mechanical advantage is also known as the force ratio. Force ratio, because it is ratio of two forces. Now, mechanical advantage is the ratio of loads L to efforts E. Now, we have that yes, it is a ratio of this and this. Now, remember that the load is measured in newtons, while the effort is measured in Newton. Because of that, Newton can cancel out Newton. The same thing with this one. So both velocity ratio and mechanical advantage, they are dimensionless because they don't have the SI unit. This one, velocity ratio, because it is distance moved by the effort is measured in meters. This one, distance moved by the load is measured in meters. Because of that, meter can cancel meter. So we now say that the velocity ratio, both the velocity ratio and the mechanical advantage, they are dimensionless because they don't have the SI unit. Now the third term we use here is efficiency. Efficiency, we can represent it like this, or we can still use EFF, efficiency, to represent this. Now this efficiency, it is the ratio of mechanical advantage to the velocity ratio. Now it is it is measured in percentage. Because of that, we multiply by 100/1. So we can now rewrite this question as you have it like this. Efficiency is a mechanical advantage all over velocity ratio times 100/1. Now this is the general formula for efficiency. This is the general formula for efficiency. In fact, that is where we now combine velocity ratio, mechanical advantage, and this. When we now combine it, it will give us this. However, we can still have that efficiency is equal to work output all over the work inputs multiplied by 100/1. Now the work output, of course, that is the product, the outcome of the work done by a machine. While the work input is work put into the machine or work done by person. Okay, so or we can say that efficiency is work done by machine over work done on machine or work done by person. So work done on machine, or I can say work done by person. They are the same thing. Multiply by 100/1. Now remember that, or recall that work done is equal to what? Force times distance. Force times distance. Now in this case, the output now is because you have the intention of raising a load. The output now is force, and that force is the load. So here we now have that work output is which is this force now. The force here is the loads times distance moved by the load. Assuming you want to raise something up, you will take the load and then the distance you move that. So which will now give us load times load distance, or distance moved by the load, however you want to put it. Now work inputs, which is work done by person or work done on the machine, work put into the machine. So which will give us that work input, and of course you are exerting some effort. Because you are exerting some effort on that machine, we now have here effort times effort distance. Effort times effort distance. In other words, we can now rewrite this equation here. We can write this equation. If we rewrite it, we now have efficiency is equal to, under work outputs, we can have load times load distance. Load times, I will use X L. All about effort now. Effort times effort distance, which is distance moved by the effort multiplied by 100. So either we have, I can call this one my equation 1. I can call this one my equation 2. We can still call this one equation 3. Now, we are going to look at some questions that can help us solve this particular problem. Now, okay, we have this question before us here, and this question says, a machine with velocity ratio 4 was used to raise a load of 1.2 kg mass through a height of 120 centimeter. If the work done to raise the load is 800 joules, calculate the useful work outputs, number 1. Second one, the efficiency. And the third one, the mechanical advantage. And here we are given that we will take a G to the 10 meters per second square. Every information given here is useful. Do not do away with any of them. Now, quickly we look at the solution. As usual, write out the parameters given. The velocity ratio here is given to the velocity ratio is given to the 4. To raise a load. Now here, the load L is 1.2 kg. And of course, since this is the load, it is given in terms of mass. All you need to do is make it to be load, or put it in the actual SI unit. And of course, we know that the relationship between force and mass, or weight and mass, is given in the relationship that says F, or we can say weight, is equal to mg. Now, see this thing is given in mass. Please convert it to kg, which will now give us that weight is weight or load is equal to mass times acceleration due to gravity, which is 10. Therefore, we now say that L is 1.2 times 10, and it will give us 12 Newton. Now, the load is now 12 Newton. Now we continue. It was raised through a height of 120 centimeters. This load was raised to a height, and now we have once we have the load, we have the height, which is this height is the distance moved by the load. Distance moved by the load XL is 120 centimeters. Remember, you need to put it in the actual SI unit, which will now give us, for us to this, we will convert it to here, we divide it by 100. If we divide by 100, it will give us that load distance, or distance moved by the load, is 1.2 meters. Now, if the work done to raise the load is 800 joules, and this work done to raise the load is the input, that means work input, work input. Work input is 800 joules. It has finished. Now, the next thing they ask us to get, we'll start with the first one. The first question says, calculate the useful work output. And we know that work output is equal to load times load distance. Load times the load distance. Therefore, it will now give us the load work output will give us load. Our load is, we'll trace it down to here, 12 Newton. Time the load distance. Distance moved by the load, XL. At the end of the day, it gave us 1.2. So 12 times 1.2. Therefore, the work output will give us, if you press the calculator there, 12 times 1.2 will give us 14.4 joules. That is the work output, 14.4 joules. Okay. The second question says, calculate the efficiency of this machine. Now, if you need to calculate efficiency, remember, is equal to MA all over velocity ratio times 100 over 1. Now, if you use this, we have not gotten our MA. We only have velocity ratio. We cannot be battling with two different unknowns. Because of that, we drop this. If we drop this one, we pick another one. Now, of course, we have work output here. We have the work input here. That relationship will go. So in other words, I will drop this one. If I drop this one, I will now say work output all over useful work inputs multiplied by 100. And this one, now with this I can get it. Okay. The efficiency here is work outputs. Remember, we have done everything about our work outputs and it gave us 14.4. We put it here, 14.4 joules all over the work input. The work put into the machine. They said work done to raise the load. This is the work done to raise the load. It is 800 times 100 over 1. Efficiency will give us, if you multiply this by the 14.4 times 100 will give us, we move this and this to give us 1,400 divided by 800. Now the efficiency will give us, the efficiency of this machine is 1.8. Remember, efficiency has no SI unit. So because of that, we'll have this 1.8 here. Now the third question says, calculate the mechanical advantage. The mechanical advantage, MA. Ordinarily, MA should have been load over effort. But if we apply this formula, we'll discover that here we only have the load. Effort not given. Because the effort is not given, we cannot use this equation to calculate for the mechanical advantage. We drop it. Each equation you apply, there are certain parameters that will require you to use one particular equation. Since this one is not applicable, the only one that is applicable, since we now have efficiency, we have the velocity ratio. What will stop us from using efficiency is equal to MA all over velocity ratio times 100 over 1. With this now, we can calculate our mechanical advantage. After calculating our mechanical advantage, we use it and that of the load to calculate whatever we want to calculate. Okay, so mechanical advantage. Efficiency, we got our, sorry, this efficiency, please, is in percentage, please. Now we have 1.8 is equal to 1.8 is equal to the mechanical advantage all over the velocity ratio. The velocity ratio is 4 times 100, which will give us 1.8 is equal to MA times 100 will give us 100 MA all over 4 times 1 will give us 4. Now, if we cross multiply at this point, we now have, I will have to rewrite this, which will now give us, if I clean off here, this one, I will have to rewrite this. This one gives us 1.8 is equal to 100 MA over 4. So this is exactly what I have here. At this point, I can cross multiply here. If I cross multiply, we'll have 1 times 100 MA will give me 100 MA equals 4 times 1.8. 4 times 1.8 will give us 7.2. Therefore, mechanical advantage is 7.2 all over 100. Mechanical advantage is equal to 0.072. No SI units. Okay, so this is how we solve this problem. We have this question before us, and this question says, a machine has velocity ratio of 5 and is 80% efficient. What effort would be needed to lift a load of 200 Newton with the aid of this machine? Now, we have this question before us. This one is simpler than the former one. And it says, so we have solution. The velocity ratio of this machine, velocity ratio is 5. Then the efficiency here is 80%. Now, what efforts? They need us to get the efforts that will raise a load of 200 Newton. Simple. Now, all we need to do is, because we have velocity ratio, we have efficiency, we are expected to get the effort. The simplest way to solve this is, if we have the general formula, the efficiency is MA all over VR times 100 over 1. And of course, this MA is just ratio of these two, the force ratio of these two. First, use one to get the MA. After getting the MA, use MA to get this. So we'll do it together. Now, the efficiency is 80%. 80 is equal to MA. Let us get MA first. MA over VR. VR is 5 times 100 over 1, which will give us 80 is equal to MA times 100 will give us 100 MA. All of that. 5 times 1 will give us 5. You can cross multiply at this point. 1 times 100 will give us 100 MA, which is equal to 80 times 5. And if we do that, 80 times 5 will give us 400. Therefore, the mechanical advantage is equal to, make MA the subject here, we'll have 400 all over 100 will give us that the mechanical advantage is 4. No SI units. Having gotten our mechanical advantage to be 4, we say, but mechanical advantage is load all over the effort. We'll put a mechanical advantage here. 4 is equal to the load. Load is 200. 200 all over E. Cross multiply. 200 is equal to 4E. make it the subject, which is the effort. Effort will give us 200 all over 4. And then 200 over 4, and of course 200 over 4 will give us 50 Newton. So the effort that will be required to lift that load of 200 is 50 Newton. Okay, this is where we'll end the lesson here. Please, this topic is a vast topic. Join me in my next video where I'll be treating the types of machine. And once we treat that, the first type we're going to treat is the inclined plane. I don't the inclined plane here, but I don't want this video to be long. So, if you have not subscribed to this channel, do well to subscribe to this channel. If you have subscribed, please follow me up. In my next video, I'll bring up the types of machines. Thank you.